Okay, so welcome back and thank you for joining me again. We were reading before chapter 7 in taking a closer look at methods and classes. So let's get back to it. Actually, I think during the last video we finished page 142 and we reviewed all of this code here. Objects being passed as arguments while hiding the instance variables. So please watch the previous videos to review that. So let's continue our reading. We got 30 pages to go and it's late. Excuse me. Let me expand this here. This is gonna help. Okay. Alright. Oh, well, for context, I guess. Use the equal to method being used in this code. Okay. That's what it is. Alright. Okay, let's move up a little higher. Okay. As you can see, the equal to method inside test compares two objects for equality and returns the result. That is, it compares the invoking object with the one that is passed. If they contain the same values, then the method returns true. Otherwise, it returns false. Now, this is comparing the values, not the address of the object in memory. If they contain the same values, then the method returns true. Otherwise, it returns false. Notice that the parameter O being equal to specifies test as its type. Although test is a class type created by the program, it is used in just the same way as Java's built-in types. One of the most common uses of object parameters involves constructors. Frequently, you will want to construct a new object so that it is initially the same as some existing object. To do this, you must define a constructor that takes an object of its class as a parameter. For example, the following version of box allows one object to initialize another. Okay. You must define a constructor that takes an object of its class as parameter. That's the same thing that's happening in this code. See, this equal to method is taking an object or a parameter of type test, which is actually the same name of the class. So basically, it's taking an object or any variable that can hold an object of type class. So I guess that's the same. And here's the code. Your box allows one object to initialize another. Excuse me. Class box, double width, height, depth. All right, let's bring the code up a little bit. Notice that this constructor takes an object of type box. Yeah. Pass object to constructor. Yeah. Constructor used when all dimensions specified. Okay. Double, double, double. So in this case, it does not take an object. Constructor used when no dimension specified. Constructor used when a cube is created. Compute and return volume. Class overload constructor too. Gray boxes is in the rest constructors. Okay, so this is the same code of before, except that the one first iteration of the method, the one instance is using an object. Okay. Box my clone, new box, my box one. And here, create a copy of my box one. So that's the constructor right there. It's taking an object right there. Isn't that cool? There. Yes, ma'am. I'm sorry. Give value of first box. Give value of second box. Give volume of Q. And give volume of clone. Mm-hmm. All right. Now you can pause the video to analyze that, but it's pretty straightforward, I think, this time. As you will see when you begin to create your own classes, providing many forms of constructors is usually required to allow objects to be constructed in a convenient and efficient manner. Okay. A closer look at passing an argument passing. In general, there are two ways that a computer language can pass an argument to a subroutine. The first way is called by value. This approach copies the value of an argument into the formal parameter of the subroutine. Therefore, changes made to the parameter of the subroutine have no effect on the argument. The second way an argument can be passed is called by reference. In this approach, a reference to an argument Sorry, I'm tired. In this approach, a reference to an argument, not the value of the argument, is passed to the parameter. Yep. Inside the subroutine, this reference is used to access the actual argument specified in the code. I think that's what happens when you pass an object. This means that changes made to the parameter will affect the argument used to call the subroutine. As you will see, although Java uses call by value to pass all arguments, the precise effect differs between whether a primitive type or a reference type is passed. Yeah, and an object is technically a reference type. When you pass a primitive type to a method, it is passed by value. Thus, a copy of the argument is made, and what occurs to the parameter that receives the argument has no effect outside the method. For example, consider the following program. Alright, let's look at the program. Okay. Primitive types are passed by value. Call by value. Okay. Right. The output of this program is shown here. As you can see, the operations that occur inside meth have no effect on the values of A and B using a call. The values here did not change to 30 and 10. When you pass an object to method, the situation changes dramatically because objects are passed by what is effectively a call by reference. Keep in mind that when you create a variable of a class type, you're only creating a reference to an object. Yeah, thus when you pass this reference to method, the parameter that receives it will refer to the same object as that referred to by the argument. This effectively means that an object acts as if they are passed to methods by use of call by reference. Changes to the object inside the method do affect the object used as an argument. For example, consider a following program. Oh, this is going to be interesting to actually see an effect. For comparison, excuse me. Here's what it means. Math j is equals to j times 2. I is equal to I times 2, and j is equal to j times 2 divided by 2. Okay, and that's what this is. Okay, so print the value before processing, and then you print the value after processing. That's all. Okay. A and B before call, and B after call. Okay. Alright. What happened here? Oh, wow, sorry. The whole machine froze briefly. Give me please per second. All right, let's continue. Um, that's actually another program that I'm running. Let's see. Okay. Um, all right. So let's bring it back up. Okay. You know what? I'm a little confused here. J is equals to. Okay. Oh wait, it's not. I'm sorry. It's not. It's not return. It's just returning the original values, not the process uh, variables inside the method. Okay, got confused there for a second. So that's why you get the same outcome. All right, it's it's referencing because there's no reference to it being saved. It's just affecting the value, and because the value was not manipulated outside of this method with the instance values, then the values from A and B were unchanged. But in the case of an object, it's not by values, by reference. So whatever is referenced is being changed in real time, because only one instance in memory exists. There can be many references to the same object, but only one instance of that object exists inside. Okay. Let's see. All right, let's read this. Thus, you pass this reference to a method. Let's read the whole thing. When you pass an object to a method, the situation changes dramatically because objects are passed by what is effectively called by reference. Keep in mind that when you create a variable of a class type, you're only creating a reference to an object. Thus, when you pass this reference to method, the parameter that receives it will refer to the same object as that referred to by the argument. This effectively means that objects act as if they are passed to methods by use of call by reference. Changes to the object inside the method do affect the object used as an argument. For example, consider the following program. Okay, and let's just bring these out and keep here. Excuse me. All right, let's keep going. Objects are passed through the reference. Okay. Int a test, int I, int j. Notice that in this case, the test constructor does not take an object as an argument. Okay, but the method does take an object. That's interesting. I wonder what I'm gonna do here. Okay. All right. Passive object. Create a new object. Give it its values 15 and 20. Before a call to the object and after the call to the object, and that method is being the reference is being passed. So it's 8 times 2 and b divided by 2. And there the changes occur. Yeah. Okay. Alright. So there you go. That's pretty cool. As you can see in this case, these actions inside math have affected the object used as an argument. Remember, oops, what happened here? Alright, we have to. Alright. Remember, an object reference is passed to a method. The reference itself is passed by use of call by value. However, since the value being passed refers to an object, the copy of the value will still refer to the same object that its corresponding argument does. Yep. All right. Returning objects. Oof. A method can return any type of data, including class types that you create. For example, the following program, the increase by 10 method, returns an object in which the value of a is 10 greater than it is in the invoking object. All right, let's look at this. Returning an object, class test. A. Returning an object, class test. Int a, test, int I. Alright. That's the object. And then test increase by 10, test, temp, new test, 8 plus 10, return temp. It's going to return the object that was created inside the method itself. Pretty interesting. Excuse me. Alright. So the object is going to carry the value of a plus 10. Okay. Okay. Interesting. Okay, but that's a clear use though. That's a pretty understandable. All right, so I'm not gonna stop here. Just pause for the sake of the video and analyze it, and we'll continue. It's because I'm already familiar with this, so I'm not gonna stop. You can stop the video for your own reading. As you can see, each time an increase by 10 is invoked, a new object is created, and a reference to it is returned to the calling routine. The preceding program, the preceding program makes another important point. Since all objects are dynamically allocated using Noob, you don't need to worry about an object going out of scope because the method in which it was created terminates. The object will continue to exist as long as there is a reference to it somewhere in your program. When there are no references to it, the object will be reclaimed the next time garbage collection takes place. Yep. Recursion. Java supports recursion. Recursion is the process of defining something in terms of itself. As it relates to Java programming, recursion is the attribute that allows a method to call itself. A method that calls itself is said to be recursive. The classic example of recursion is the computation of the factorial of a number. The factorial of a number n is the product of all the whole numbers between 1 and n. For example, 3 factorial is 1, 2, 3, or 6. Here's how a factorial can be computed by use of a recursive method. Oh, this would be fun. Oh man. A simple example of recursion factorial. This is a recursive method. Int fact, factorial, int n, int result. Alright. If n is equal to return 1, result factorial is n minus 1 times n. Return result. Wow. N minus 1 times n. That's pretty cool. But why is it n minus 1? 2. So this is 3, it will be 3 minus 1 is 2, times 3 is 6. If it's 9, 8, 8 times 2. Oh, because, I see. I get it. There's no point in multiplying 8 by, times 1. Class recursion. Public static void. Factorial f new factorial is fact 3, fact 4, fact 5. Oh, that is so cool. That is so cool. And by the way, it's calling itself in the middle. Its result is equal fact and -1 times n. Yeah, that's pretty cool. The output from this program is shown here. 6, 4 is 24. Factorial 5 is 120. That's pretty cool. If you're unfamiliar with recursive methods, then the operation of fact may seem a bit confusing. Here's how it works. When fact is called with an argument of 1, the fact function returns 1. Otherwise, it returns the product of factorial n minus 1 times n. To evaluate this expression, fact is called with n minus 1. This process repeats until n equals 1, and the calls to the method begin returning. To better understand how the fact method works, let's go through a short example. Alright, let's go back here. When you compute factorial 3, the first call to factorial will cause the second call to be made with an argument of 2. This invocation will cause factorial to be called a third time with an argument of 1. This call will return, which is then multiplied by 2. The value of n in the second invocation. Yep. This result, which is 2, is then returned to the original vocation factorial and multiplied by 3, the original value of n. This yields the answer 6. You might find it interesting to insert printline statements into factorial. We will show at what level each call is and what the intermediate answers are. Yeah, that should be really fun. Let's see. Okay. When a method calls itself a new local variable, when a method calls itself, new local variables and parameters are allocated storage on the stack, and the method code is executed with these new variables from the start. As each recursive call returns, the all local variables and parameters are removed from the stack, and execution resumes at the point of the call inside the method. Recursive methods could be set to telescope out and back. Recursive versions of many routines may execute a bit more slowly than the iterative equivalent because of the added overhead of the additional method calls. A large number of recursive calls to a method could cause a stack overrun. Because storage for parameters and local variables is on the stack, and each new call creates a new copy of these variables, it is possible that the stack could be exhausted. If this occurs, the Java runtime system will cause an exception. However, this is typically not an issue unless a recursive routine runs wild. Another thing that happens that I should say, pause in here. Another thing that happens that I should say is, what I noticed is that I made a program. I'm choosing a menu where you could create like vehicles and choose their options, and I was using recursion like this. Is that if you have to back up to the original menu, you got to make sure to either use a label or the return or the exit keywords. Because if you just break out of a loop or continue out of a loop, you're not going to go all the way back to the original. So it may ask you to re-input some of the stuff. And I was caught in that recursive error, well, semantic error technically, no runtime error. Um, until I could think it through and figure out, oh boy, no wonder. It's because it's escaping only one scope back. So that's good to know. All right, going back to this here. Okay. The main advantage of to recursive methods is that they can be used to create clearer and simpler versions of several algorithms that okay, that can their iterative relatives. Oh, okay. For example, the quick sorting algorithm is quite difficult to implement in an iterative way. Also, some types of AI-related algorithms are most easily implemented using recursive solutions. When writing recursive methods, you must have an if statement. Let me bring this up a little bit. Okay. You must have an if statement somewhere to force the method to return without the recursive call being executed. If you don't do this, once you call the method, it will never return. This is a very common error in working with recursion. Use printline statements liberally during development so that you can watch what is going on and abort execution if you see that you have made a mistake. Yeah. Here's one more example of recursion. The recursive method print array prints the first I elements in the array values. All right, let's see. Another example that uses recursion, class rec test int values. All right, let's see. Let's bring that up. Rec test values, new int, okay. I display array recursively, void print array I, if I 0 return, else print array. There's a recursion right there. I minus 1. Okay. Recursion 2. Class recursion 2. Print static void. Okay. Rec test. New rec test 10. Okay. We go. That's pretty cool. That is in fact pretty cool. Values. So basically this right here is adding values to the array. And then the if statement adding the values, and then the print array is doing the recursion. This program generates the following input, and here it is. Nice. All right. Introducing access control. As you know, encapsulation links data with the code that manipulates it. However, encapsulation provides another important attribute, access control. Through encapsulation, you can control what parts of a program can access the members of a class. By controlling access, you can prevent misuse. For example, allowing access to data only through a well-defined set of methods, you can prevent the misuse of that data. Thus, when correctly implemented, a class creates a black box which may be used. Oh, excuse me a second. Okay. Thus, when correctly implemented, a class creates a black box which may be used, but the inner workings of which are not open to tampering. However, classes that were presented earlier do not completely meet this goal. For example, consider the stack class shown at the end of chapter 6. While it is true that the methods push and pop do provide a control interface to the stack, This interface is not enforced. That is, it is possible for another part of the program to bypass these methods and access the stack directly. Of course, in the wrong hands, this can lead to trouble. In this section, you will be introduced to the mechanism by which you can precisely control access to the various members of a class. Alright. How a member can be accessed is determined by the access modifier attached to its declaration. Java supplies a rich set of access modifiers. Some aspects of access control are related mostly to inheritance or packages. A package is essentially a grouping of classes. These parts of Java's access control mechanism will be discussed in subsequent chapters. Here, let's begin by examining access control as it applies to a single class. Once you understand the fundamentals of access control, the rest will be easy. Okay. Note, the modules feature added by JDK9 can also impact accessibility. Modules are described in chapter 16. Okay, so we're a long way to go before we get there. All right, so Java's access modifiers are public, private, and protected. Java also defines a default access level. Protected applies only when inheritance is involved. The other access modifiers are described next. Let's begin by defining public and private. When a member of a class is modified by public, that member can be accessed by any other code. When a member of a class is specified as private, then that member can only be accessed by other members of its class. Now you can understand why main has always been preceded by the public modifier. It is called by code that is outside the program. That is, by the Java runtime system. When no access modifier, oh wow, that is very good explanation of the abstract going on there. Very clear. When no access modifier is used, then by default the member of a class is public within its own package, but cannot be accessed outside of its package. Packages is discussed in chapter 9. Okay. Sorry, I'm yawning, so I have to just mute myself briefly. Okay. In the classes developed so far, all members of a class have used the default access mode. However, this is not what you will typically want to be the case. Usually, you will want to restrict access to the data members of a class, allowing access only through methods. Also, there will be times when you will want to define methods that are private to a class. An access modifier precedes the rest of the member's type specification. That is, it must begin a member's declaration statement. Here's an example. Public int I or private double J, private int method int A, etc. Okay. To understand the effects of public and private access, consider the following program. This program demonstrates the difference between public and private. Class test. Int A, default access, public in, public access, and private int C, private access. Methods to access C. Void set C. Set C. Int I C equals I, or I is assigned to C. Int get C returns C. It gets this value. Alright, let's go scroll up. Class access test. Okay, test object and test. These are okay. A and B may be accessed directly. This is not okay and will cause an error. OBC is assigned to 100. Okay. You must access C through its methods. Alright, so up C, and okay. and a setter and a getter method. As you can see, inside the test class, A uses default access, which for this example is the same as specifying public. B is explicitly specified as public. Member C is given private access. This means that it cannot be accessed by code outside of its class. So, inside the access test class, C cannot be used directly. It must be accessed through its public methods, set C and get C. If you were to remove the comment symbol from the beginning of the following line, then you will not be able to compile this program because of access violation. To see how access control can be applied to a more practical example, consider the following improved version of the stack class shown at the end of chapter 6. This class defines an integer stack that can hold 10 values. Class stack. Now, both stack and TOS, topo stack, are private. This means that they cannot be accidentally or maliciously altered in a way that will be harmful to the stack. Oh, so let's see it on here. Private int, okay, stack, and then int topo up stack, okay. Initially topo stacks, okay. Stack is thing only one. Push an item onto the stack. Push and, okay. All right. All right, sorry. Okay, this is the same program as before, so you can kind of pause and see whether oops, and having an issue here. Okay. All right, so pop an item from the stack. Oh, there's something wrong with the preview app. Excuse me a second. Okay. Stack underflow. Stack TOS, and then reduce it. That's pretty cool. Okay, my system is running slow, so hopefully the audio doesn't mess up. Alright, so let's go ahead and keep on reading. I stopped too much because in this 40 minutes I only got 10 pages read. That's very little. We're gonna have to read a little faster in the next one. Okay, and it looks like the system is just getting slower. Yeah, it is slowing down. I don't know. I don't have anything else. Hold on. Okay, I don't see anything else running that will cause this issue. Let me turn off TextMate terminated because truthfully I'm not doing anything with it at the moment. So we're gonna shut down TextMate to free some memory. So we're gonna do. Alright. And let's come here and hopefully that will help. You know what? Hold on, let me check one more thing. Memory. Okay. Ooh, a 78%. Oh my god, what is using so much memory? Something here is using too much memory and I don't know what it is. Let's see. Okay. Alright. Let's try it one more time. Back to 77. That's still a lot. Should stay under 70%. Oof. Hopefully the audio doesn't mess up. That's a whole hour that I'm gonna have to trash a video. Or mute. Alright. As you can see now, both stack, which holds the stack, and TOS, which is the index of the top of the stack, are specified as private. This means that they cannot be accessed or altered except through push and pop. Making TOS private, for example, prevents other parts of your program from inadvertently setting it to a value that is beyond the end of the stack array. Yeah, by the way, the reason why it has a it's reduced with a negative is because when it's used to for an index, the number 9 is the 10th index of an array, because the first index of an array is the number 0, so it's 0 1 2, so therefore you have to reduce the number to match the last array. Okay, alright, let's see. The following program demonstrates the improved stack class. Try removing the commented outlines to prove to yourself that the stack and TOS members are indeed inaccessible. Well, I'm just going to show you the code, but you can pause the video and analyze the code, because I already know this kind of things, and I already know what's going on in this code. Okay, so just pause the video, if you please. Alright, let's keep going. Although methods will usually provide access to data defined by a class, this does not always have to be the case. It is perfectly proper to allow an instance variable to be public when there is good reason to do so. For example, most of the simple classes in this book were created with little concern about controlling access to instance variables for the sake of simplicity. However, in most real-world cases, you will need to allow operations on data only through methods. The next chapter will return to the topic of access control. As you will see, it is particularly important when inheritance is involved. Alright. Okay, so understanding static. Okay, there will be times when you will want to define a class member that will be used independently of any object of a class. Normally, a class. Oh, that is an interesting way to put it. When you want to define a member that will be used independently of the objects of the class, I never thought about it like that. I mean, it's clearly what it is, but I never thought about it in that way. Normally, a class member must be accessed only in conjunction with an object of its class. However, it is possible to create a member that can be used by itself without a reference to a specific instance. To create such a member, proceed its declaration with the keyword static. When a member is declared static, it can be accessed before any object of its class are created, and without reference to any object. It can declare both methods and variables to be static. Okay. The most common example of a static member is main. Main is declared as static because it must be called before any object exists. Instance variables declared as static are essentially global variables. Yep. When objects of its class are declared, no copy of a static variable is made. Instead, all instances of the class share the same static variable, and that will be the same address. Location and address and location. Most declared methods, declared as static have several restrictions. They can only directly call other static methods of the class. They can only directly access static variables of their class, and they cannot refer to this or supper in any way. The keyword supper relates to inheritance and is described in the next chapter. So now you know they are their own grown men. All right. Okay. If you need to do a computation in order to initialize your static variables, you can declare a static block that gets executed exactly once when the class is first loaded. The following example shows a class that has a static method when no some static variables and a static initialization block. Hmm. Ooh, this is very nice. Okay. As I'm repeating that in my mind, I think it's good to absorb that clearly. If you need to do computation in order to initialize your static variables, in order to initialize them, you can declare a static block that gets executed clear exactly one when the class is first loaded. Hmm. The following static block shows a class that has a static method, some static variables, and a static initialization block. Alright, so now let's look at it in practice. Demonstrate static variables, methods, and blocks. Class use static, static int A equals assign 3, static int B, non-assignment, static void, met int x. Okay. X is X, A is A, B is B. Okay. Hmm. Static system, static block initialize, 8 times 4. Okay. Static magnum void main. Okay, math 42. Okay. Wow, I am so tired. I'm not even kidding. Alright. As soon as your static class is loaded, all of static statements are run. First, A is set to 3, then static block executes, which prints a message and then initializes B to A times 4 or 12. Then main is called, which calls met, passing 42 to X. The three point statements refer to two specific variables A and B, as well as the parameter X. Here's the output of the program. Let's look at the output of the program. Yep. Outside of the class in which they are defined, static methods or variables and variables can be used independently of any object. To do so, you need only specify the name of their class followed by the dot operator. For example, if you wish to call a static method from outside its class, you need to do so using the following general form: class.method, that's class name dot method. Okay. Here, class name is the name of the class in which the static method is declared. As you can see, this format is similar to that used by non-static methods and through object reference variables. Static variables can be accessed in this way. In the same way, by using the dot operator on the name of the class. This is how Java implements a control version of global methods and global variables. Okay, here's an example of inside main, the static method called callme and the static variable b. Okay, here's an example. Okay, to this class name static demo. Okay. All right. So we're gonna do. You can pause the screen to see the class. Okay. I'm going to continue this tomorrow because I think I have to take a nap of at least 40 minutes before I can keep studying because I am extremely tired. We're about halfway through our reading. We started at 43, right? And we are at 55. Oh no, so we got at least 3 more pages to go. But we can do it. We'll take advantage of the time best. We'll take advantage of the time best when we get to um, when I get to nap a little bit because I am very tired. So we left at page 1, at the end of page 154. We're gonna get started on the next video when I come back, and we'll finish our reading tonight. I gotta set an alarm and take a nap. Be right back.